programming objectives. That's right. Any good with
okay. So I want to talk about the functor schism, and this is the fact that we actually have two quite different semantics for functors in ML. So functors, are the highlights of the ML module. It's one of the highlights of the ML module system. But I'm not sure how many people are aware that there are actually two quite different semantics. So one is called the generative semantics for functors, and that is kind of like the traditional, original way of doing functors, and is what SML is doing. So there, when you have a functor that defines some abstract types and you apply it several times, then you get back a fresh set of abstract types with each application. And in Ocaml, you have the notion called applicative functors. So there, when you apply the same functor to the same argument several times, you get back the same abstract types. So let me demonstrate that with a brief example. Standard example is some set functor, right? So you can define set signature in ML, and you can define a signature for an order type, and then you can write a functor, something like that. So ignore the implementation. The interesting thing is the type, and in particular, you return something where the element type is transparent, but the set type will be abstract. So with the generative semantics, of course, you can instantiate this functor. So for example, by applying it to some pre-existing int structure. And then you can build sets by using the functions it exports. But the interesting thing is what happens when I apply it twice. So does this, does a mixed use of the two modules still type check? And under generative semantics, it doesn't. So because the two instantiations will produce incompatible set types. So that won't work. And under the applicative semantics, that will work. So the type system sees that both functor applications are the same syntactically, so it will equate both types. And more specifically, we'll do that by equating both types to the projection out of the application of the functor. So that means you can actually talk about the type without even having an instantiation by allowing these form of extended type paths. And yeah, so most of the literature on modules, on ML modules and functors actually usually uses the generative semantics because it's somewhat simpler and also what was there first. And there's like 4 main works that treat applicative functors. So the first one is the original one by Xavier that introduced the notion, and which is the foundation for Ocaml basically. And then there is the work by Claudio Russo, which combines generative and applicative functors in one system. At least the second version of that does that, and which is what is implemented in Moscow now, and which is based on a somewhat more type theoretic explanation of the same thing. And then there are like more follow-up works, which I won't go into in detail, but which also all combine applicative and generative functors in one language and try to make the semantics somewhat more precise. But they are not implemented in any language you might have encountered. So that's what I want to talk about here, applicative functors mainly. So why do we have these two different semantics, and what are the issues that probably exist with reconciling them into one thing? So in particular, I want to talk about the issues with applicative functors, and why all of the semantics I've shown there on the previous slides actually don't really provide what you want. And yeah, the second part of the talk then will be a kind of proposal for new semantics that we think is the right thing. So before I talk about the issues with applicative functors, let me briefly motivate why you even want to have them in the first place, because that's also a question I sometimes get, like last night. And in the literature, the motivation is usually some weird examples with higher order functors, and you might think, why should I care? And that is a fair question, although in practice it is that this actually occurs in disguise when you talk about separate compilation. So the model for separate compilation on the theory side kind of for ML is that you consider a compilation unit as a functor body. and the imports of your module are basically the functor parameters. And when you have a compilation unit that imports a functor, then you have basically written a higher order functor. So there are examples in practice where actually these, like the kind of academic examples from the literature, you can translate into this scenario to make that more like something you might recognize. I will give like a very simple example here, which I think everybody sees why applicative might help there, and that is thinking about map functor. So the other canonical generic data structure that every ML library has as a functor are maps. So here's a very simple signature for that. And so far this is all fine, you can just implement it, but now assume I want to extend this signature with a function that returns the domain of the map. And you want to do that as a set, obviously. So how would you do that? What type would you give to that function? Well, with a generative semantic, so the idea is you want to use the set functor I introduced earlier, obviously. With the generative semantics, there are basically only two ways to do that, and they roughly amount to either importing or exporting an instance of the set functor to do this thing. So one variant is that your implementation of map actually does an instantiation of the set functor and then exports that type in its signature. It has to export it because otherwise no client of that signature could use the set, right? And also it's not sufficient to export the type, you actually have to export the full module. And what's the problem with that? Well, just think about the scenario where you have several abstractions of this kind, which all need to use set in some way. They will all define their own instance, and then you have some kind of diamond import somewhere else, some other client that wants to combine them and sees like several different incompatible set types, right? And has to convert all the time. So that is not really what you want to do. So kind of the dual thing is we don't export the set thing, we import it. And that in terms of functors means we turn it into an argument of that functor. Then you can apply these different things with the same instance, and this looks fine so far. But here the problem is that when you start piling up abstraction layers, then you start accumulating additional arguments like that. And when you drive that kind of approach to the logical conclusion, then you end up with what in the early days of ML modules was called the closed functor style, where you basically only implement functors that don't use anything from the environment, but everything turns into an argument. And if anybody of you has ever tried to do that, or looked, for example, at the source of the ML kit in its early days, which tried to follow this style, then you will quickly realize that this is practical. So, yeah, both these variants basically lead to a pollution of your interfaces, are not very nice to use in practice. But with generative functors, this problem goes away, because here you can just refer to the type in this way without actually having an instance. So you neither have to import or export it. The only minor thing you have to do is, instead of just specifying the key type there, you actually have to specify the module, because otherwise you can't write this application. But that is really a minor thing. The interface of the functor itself stays clear of further complications, and this doesn't pile up. So that's why I think actually applicative functors are really a nice thing to have, and they help in terms of modularity. And you can think of other examples.
On that example, would that actually work in Ocaml applicative functors? Because the module I don't know why. I believe you. But the module key on the inside in the signature is presumably, like, you could have like module key equals key, like, isn't that module key a new module distinct from the one that was passed in the argument?
There must be a typo in with type constraint. It should be with module.
With module. Oh yeah, sorry, that's a typo. That should be key.
Oh, I see.
Sorry, yeah, I forgot to fix that. Right.
I guess in the implementation of this.
In this functor, or where?
Yeah, in the implementation of the map functor.
Yeah.
That module key that you get. You get by saying,
That would just be the argument you get. So you just say in the body module key.
we do module key equals key.
Yeah.
But that's a new module, isn't it? From the point of view of particular functors, if I have module A and I have module B equals A, and I apply something to A and apply something to B, they do not, you do not get a problem. Like that I'm pretty sure of, because I've stuck my tongue.
It's just an assignment, but it's the same, it's not an application itself. You just module equals.
So you're talking about the issue of renaming and that might, so I mean, there's actually one of the things I might come to later, that the notion of type equivalence or modular equivalence of Ocaml is a bit restricted.
Right, the equivalence, yeah, that's exactly what I was pointing at.
So what I'm aiming at certainly is semantics where this is no issue.
Okay.
So functors are useful, I would claim. But what are the issues? So unfortunately, applicative functors are quite delicate once you get into the details. And I want to walk through a few examples that show you some of the issues. So the first one has to do with type soundness, actually, and in particular in the presence of first-class modules, or technically more accurate, modules as first-class values. So both Moscow ML and more recently Ocaml have this as a feature, so you can pack up a module as a first-class value. Like here, for example, so you can define a signature, and then you can have two structures which you wrap up as a value under the same signature. So, and this you can pass around, obviously, in a first-class manner, but when I'm now writing a functor, I could be tempted to try to do this. So I have a reference P that contains one of these packages, and I have a functor that unpacks the content of that thing and returns it. And you probably already see where this is going. If I try to do that twice and change the content of P in between, and if I was also having an applicative semantics which says the types defined by the same functor application is actually the same, then this would, of course, blow, right? Because I could then apply one function from one to the other. So this is a problem. Applicative semantics can break type safety. The way Moscow ML and Ocaml get around that is only by restricting the use of unpack in quite an unsatisfactory way. So in Ocaml, you can't use unpack in a functor, basically. In Moscow ML, the restriction is even more severe because their unpack is a closed scope call level construct. So you can't even use it on a module level at all. And obviously, neither is really quite what you want. So this is, yeah, one thing. But there are more subtle things. So the next thing is about abstraction. And I should say all these are like kind of more well-known examples, more or less, at least to people who are familiar with all this topic. So let me give you possibly the simplest example of a stateful ADT. And that is an ADT for abstract names. So the only operation you have there is for creating a fresh name, and you can compare two names for authority. And like the straightforward implementation is one where your name is just an integer, and you have a little counter that you just need to create a fresh one. And one thing though is I want to define this ADT as a functor so that I have the ability to actually generate different sets of names in my code. Which is something you do at least in standard ML. You find abstractions like that. But now, well, what happens under an applicative semantics, obviously, when I apply the same functor twice, it returns the same type. But when I now apply the new function of the two separate modules, they have two copies of the state, right? But only one type associated to them. So this actually breaks the invariant of my implementation because the new function doesn't actually guarantee freshness anymore. Because in this example, A and B will be the same.
It's actually more subtle than that. In Ocaml, if you do sig n, close brackets, then they're different.
Right.
But if you module unit equals sig n.
I come to that later, right? So for Ocaml to actually force applicative semantics there, you would have to define a module unit that is empty and named. But same thing. So this is actually quite a bit more subtle, but it's also a sort of soundness violation, if you want. Yeah. So, but that has to do with state, right? So with impurity. So what about pure functors? Is there an issue as well? And depending on how exactly you do it, there is. So consider these applications of the set functor. And most of the semantics I listed earlier would actually equate the set types generated by these two functors.
Why? Why there are different inputs?
Because they only consider the type components.
Not Ocaml.
That's a good point, but I'll come to that in a minute. So obviously when you equate the two and then you can apply the add method, for example, from mixed implementations, then that will just totally mess up your internal invariance of the set representation, and like a membership test might suddenly fail because the search tree has no invariant. So that's another way in which applicative semantics can break abstraction safety even for pure functors, if you're not careful about the way how you define type equivalence. So there was the comment already that in Ocaml this cannot happen, and that's correct, because in Ocaml there is this restriction that you only get the same type when you actually apply a functor to something that doesn't syntactically contain a structure, like here. So in Ocaml I would have to name the two structures to have applicative semantics, but then I would have to name them differently, obviously, because they're not the same expression. Of course, the downside of that is also that in Ocaml, if both the arguments actually were the same, then I still have to name them, and they still wouldn't give the same type. But that is maybe more minor point. But yeah, so in Ocaml, this actually doesn't type check because the types are not the same, and technically that is because a path of that form is not allowed. So basically, the Ocaml type system just silently drops the equivalence between the result of the functor and its argument of the floor. So you lose it. But is that enough? I claim we can still defeat Ocaml. And what we do is this. We just introduce right? Just a simple, just one level of indirection more, and you can still produce the same effect. Arguably, you have to work a bit harder, but still, abstraction is violated there. And basically, what's going on here is that the problem again goes back to impurity. So Ocaml allows an impure functor path.
There's something to do with applicative functor. Like, if you give set an order of type where the order changes randomly over time, this is just first order functors, generative and whatever, but it's already broken, right?
So you say like an order function that is itself impure.
Yes, yeah, exactly.
Right.
Like, yeah, well,
so
indeed, yes.
yeah, that's true. But the thing is, so that is something you have to fix on the source on the call language, right? So you could imagine that your call language allowed you to distinguish between pure and impure functions, and then in the argument signature for the functor, you could require a pure function.
Right.
And if you did that, then you could still do this. So it's kind of a separate problem. Ultimately, you want to fix both.
Itself would still be pure. No, never mind.
Right. So yeah, what I said, a functor that is impure, allowing that in a type path can break abstraction safety even of the pure functors. So what I want to do in the rest of the talk is propose an alternative semantics for functors that we claim solves all these problems, and maybe give a little sketch, depending on how much time is left, on how we formalize that. So the framework we're using here is our effing module semantics, and so we recently finished a journal version of that, and that contains an extension with applicative semantics. I won't be able to show you much here, but that is like the inspiration for this talk. So the proposal for fixing that, first of all, the most important observation maybe is, in an impure language like ML, yeah, you can have generative functors, you can also have applicative functors, but it doesn't make sense to have applicative functors only, so that's what I would say. So if you want to have applicative functors, then you need both. Moreover, what you really want is, you want that only functors are deemed applicative that are pure. And what I actually want to suggest here is that we put away with this weird terminology of applicative and generative. What we're really talking about are just pure versus impure functors. And then you also won't confuse the Haskell people anymore when you talk about applicative functors. But of course what that implies is that the type system has to track purity of modules. And the other thing we have to do is we want to track, we want to refine the notion of module equivalence and thereby type equivalence, so that it only equates modules where both types and value components are equivalent. And what that means is that we actually have to track the equality or the identity of types and of values in some way. And of course we want to do that avoiding going to dependent types, so we need to use some approximation. So to deal with purity, what we propose is, so first of all I should say all the previous approaches that combined applicative and generative functors mostly did that by introducing two forms of functor expression. Or in the case of Dreyer et al.'s Popple paper, they even had like two different forms of sealing, so signature ascription. And we don't think any of that is needed. If you track purity, you can just let the type system make the distinction itself. So you just say a functor is a pure functor if it doesn't unpack a first-class module, if it doesn't apply an impure functor, less local. And if all the value bindings, so there we are reusing a notion that's already there in ML to approximate purity of value bindings, we just reuse the notion of non-expansiveness, so the value restriction. So if all your value bindings obey the value restriction, then we deem a functor expression pure. But of course on the type level you have to distinguish between pure and impure functors, so you have to introduce two different functor signature types. And for values what we do is, this is only more or less on the semantic level, but the idea is that we assign abstract identity to each binding, to each variable that is bound in a functor or in the module. And we track that in the type system. And in particular, when you have a binding that is merely a renaming of some other thing, then you retain this identity. But all other bindings introduce fresh identities. And in signatures, you basically have abstract identities for all values that are specified there. And technically, the way we do that is using phantom types in our semantics. So every value binding is associated with a type variable that you then quantify over, for example, in a signature in the same way you do with abstract types. And you can really handle it in a pretty consistent manner. Another way to look at this idea is that we're basically reintroducing the notion of structure sharing that existed in early standard ML, where it was realized by a very operational way using stamps. So here we're reconstructing it in a more type theoretic manner using type variables, phantom types, and we refine it to work on the granularity of individual values instead of whole structures. So if you've seen that before, then this might be some resemblance. So overall, what we're doing is we are almost not changing the language. So this is like roughly an idealized form of ML, and the only thing we are adding is pure functor signatures. So I won't really have time to go through the formalization here, but we did that, as I said, in the FA modules approach. And very briefly, the FA modules approach is one where we take the syntax of modules I just showed you on the previous slide and elaborate it into vanilla system F omega. Extended with records to represent structures, but that's it. So you translate every signature into an existential type, and you translate over every module into an F expression with an existential type. And then the invariant of that is that, well, you produce well-formed things. And that is basically the summary statement of the semantics. And I use the sigmas here, so these are just special system F types, and the interesting ones here are functors. So in the generative case, the functor looks like that. So you have a going from one signature to another, and all the abstract type variables in the argument are universally quantified. The ones in the result you bind by an existential quantification. Because that's in the result, you get fresh ones each time you apply it. And now the only change we do here on the first level is that we also infer a purity annotation, so a very simple effect, which is either pure or impure, and we extend slightly our semantic signatures. So the thing up there is to track value paths, and then you just have the annotation on functor types. And the main idea here is that an impure functor has the same form as before, but for a pure functor, we follow the idea that was originally invented by Biswas and which Claudio used in his thesis to realize applicative functors. The main difference here is that the existential quantifier is no longer in the result, but you have to lift it once. Okay, so my time is up, so that's basically the idea. Let me go to the conclusion. So applicative functors are really delicate. I hope I convince you of that. And the takeaway message from this talk should be that you should really think about applicative versus generative functors as pure versus impure. That's really the essence of it. And module equivalence should be type equivalence and value equivalence. And yeah. If you're interested in all the gory details, they're out in the paper, which is not on my webpage yet, but should be very soon.